to ask questions, please. Tariq said that he's very pleased to have questions during the talk, which I think makes for a much more engaging discussion. So again, students, please ask questions. And of course, other students, staff, and faculty are welcome to as well. So with that, I just wanted to introduce our speaker. He did his PhD work at the University of California at San Diego. Also did a postdoc at CCEL MIT. And as I mentioned, is now a professor in system engineering and computer science at the University of Virginia. And he's going to give a talk today on a very interesting subject, something I think is really, really important kind of in a future looking sense, entitled Toward Fluent Collaboration and Human Robot Teams. So with that, please.
Yeah, thank you very much, Doc, for the introduction, and I'm very excited to be here. Today, I will be talk a little bit about the work that we're doing in here in my lab. I'm leading the collaborative robotics lab, and my talk will be mostly focusing on how can we make robots to work alongside human in teams. So when we are thinking about robots, I think when we say robots, many of us are thinking robots like this. Robots are doing all sorts of stuff. Robots are working alongside us. Robots are cleaning our house. Robots are interacting with us verbally, non-verbally, and they're fluently communicating with us. And even many cases, we also think that robots are coming to destroy us, right? And why is that? Why we are thinking robots are like that? Because like science fiction and movies, that's how we think the robot should be. The robot should be in our environment. Robot should interact with us. Robot should help us. Robot will solve all of our problems. But when we are actually looking at the robots in real life, what we are seeing robots are like this. In the factories, many of you probably have seen this already, that robots are building cars in the factories where big giant arms are moving parts around. Or many of you probably have seen the Amazon warehouses where robots are moving around and moving big shelves from various places. So these robots are very precise and doing their stuff exactly on time, and they're repetitively doing the same task over and over again, oftentimes probably for months without any problem it faces. So there is like, for example, if you're taking the example that I'm showing in the top, in the car manufacturing industries, when we're seeing that big robots are building car bodies, if you're looking down the line, exactly in the same assembly line, we can see that humans are working as well. So at the earlier part, robots are building the bodies of the car. And if we are moving forward in the same assembly line, we can see that humans are assembling various other parts to that car to make the final product. But we are seeing something which is not, when we think about robot, we envision. What we are seeing in this kind of environments that there is a physical barrier between a human and a robot. And this physical wall is literally a physical fence that where humans and robots cannot interact among themselves together. There are many reasons for that, and why we think why we go with this setup where humans and robots are separated, whereas in our thinking, when we are thinking robots, and we are thinking robots actually in our environment. The fundamental reason for that, these robots are not capable of working with humans. That is the fundamental reason where we need to have a physical barrier there. Because this robot cannot perceive human, cannot predict what the humans will do, cannot make any decision based on human motion and human actions. So essentially, it boils down to these robots are not ready to be in our environments that we all hope that the robots would be in the future. So to address this problem in our lab, we are trying to try to address this question: how can we build robots that can work with people? We want to break this wall. We want to make the human and robot a same team, member of the same team, instead of two separate teams in the same line. Why we want to do that? We want to do that because we posit that if we can build a single team of humans and robot, then the team can achieve something that's neither the robot nor the human can achieve alone. So as I mentioned, I lead the collaborative robotics lab here at University of Virginia. Among several projects that we have in the lab, it boils down to these three main areas that we are interested in. First is close proximate collaboration. That means how can we enable robots to be in close proximity with human. This is a challenging task in general because it not only we need to ensure the safety of the people, but we also need to make sure that we are planning the task for the robots in a shared, physically shared environment with the human in real time. So it makes the close proximity interaction is very challenging for a robot to achieve. Then in our group, we are also very much interested in developing and building robots for social and physical assistance. By social and physical assistance, what we focus on are socially assistive robots could help the people with various disabilities, like emotional or cognitive disabilities, to help them help and support them to get like somehow with their disabilities. For example, a robot in a classroom settings can help students with cognitive disabilities to practice this learning materials over and over again to help them better grasp the content of the learning materials. We also are focusing on physical assistive robots, and this kind of robots can help, like in an example that I am showing here, can help the people with physical disabilities with their locomotion and in many cases with their decision making and cognitive stuffs as well. We are also very much interested in human robot trust, and human robot trust is very important in the sense that now we are, as we are thinking that robots will be entering our environment, the optimal utilization of all those robots depends on how much trust we are putting on those robots. Just to give you an example, like we all know about the Tesla accident, which happened a couple of years back. And why did that happen? Tesla always instructed the drivers to put their hands onto the wheel, onto the steering wheel, right? So why did that accident happen? Mostly because like the perception system failed, but also because the person who was driving that car was in the sense of belief that the robot, in this case the autonomous car, could detect those obstacles and drive safely. So the person was over trusting the system, and one of the reasons for those accidents was the over trust on those autonomous system. So that actually indicates why a calibration of trust is needed, because in this case, if the system had some sort of capability to understand that the human is over trusting the system should somehow notify the user that, okay, you are trusting me more than what I am capable of, so you should not trust me that much. Or in the flip side, if the person is not trusting the systems enough of its capability, then the person might use the system less what the system is capable of. So we think that as systematic trust evaluation and calibration into the team is very important to enable a fluent team.
So, can I ask a question there?
Yes, absolutely.
I'm just so curious because when I think of trust as a two-way street, right?
Absolutely, yes.
And it's interesting here, right? Because it's just the human trust of the robot's actions, right? And that then there's mitigation or mediation that the robot might be programmed to do to help improve that trust relationship with the human. So I wonder if there's something different in terms of what people traditionally think of as a trust model versus when we have a robot in the middle of it.
Yes, absolutely. Look, that's a very important question, right? Like as you mentioned, like trust is bidirectional. It is not only like how much trust the robot we should put onto the robot. Also, robot needs to know and calibrate that trust level, right? So in our recent work, what we did a study recently, which was presented actually last week at HRI. So that study was about like how what strategies robots can use to gain its trust back. What does that mean? Like, say, I, as a human, are thinking this robot is capable of doing something. That means like I'm sort of trusting the robot can do that. But robots are not always capable of doing everything. So robots will fail. If the robot fails, what strategy the robot can take to mitigate that failure? How can robot get its trust back a little bit? And we found that like human-like humor might be a good strategy for robots to actually social robots to get their trust back. I absolutely agree with you, Doc. Like that. It's bidirectional. So it's not only the robot is measuring how much we are putting trust on, but also it needs some sort of capabilities to gain it back. Is that the question that you were asking, Doc?
Yeah, absolutely. Sorry, I was talking to a muted.
Oh, sorry. Yeah.
Thank you.
Yeah, no problem. Yes, so for this talk, I only will be focusing on the close proximate collaboration work that we are doing in our lab, but I'll be more than happy to discuss about the other projects offline as well. So now let's talk about like the close proximate collaboration. What do you need the robot to do to enable close proximate fluent collaboration? From the very high level, if you are taking a bird's eye view, like from the very high level, the robots need perception. Robot needs to know what's around it. Then based on that, robot needs to make prediction. In this case, like if we are thinking about human robot, then we are thinking that robot needs to perceive human. Robot needs to understand what the human is doing, and then robot needs to also predict like what the humans will be doing in the time and space. And that is a very important step for the robot. Otherwise the robot would be always reactive. We don't want always a reactive robot which like reacts upon human's action. Rather, we want the robot to predict what the humans is going to do, so that like the robot can then at the last step collaborate with the person. So just to give you an example, in the human-human collaboration, if I am extending my hand, right away the other human knows that like I'm extending the hand to maybe shaking for a handshake, and the person also starts extending their hand at the same time. This is because like the human in their mind, in the brain, they're also cognitively predicting what actions the other agent of the team is going to do, so that like I can perform an action to support or in general, like making a decision and performing an action to support that agent. And this is exactly the same sequence of things that human also does: perceive, predict, and collaborate. In our lab, we are trying to enable human-robot collaboration by also following these steps. We are working on perception in various degrees. We are also working on prediction and also making the fluent collaboration into the teams. And I will be talking a little bit about all this chain that we are working in our lab. So let's first talk about perception. So as we are thinking about human-robot collaboration, in our case, by perception, we are focusing on human activity recognition, whether we can make the robot to recognize what activity the human is currently doing. To address this challenge, we are taking a little different route than most of the computer vision community are doing. They are doing also human activity recognition, but they're doing mostly from the unimodal sense. What does that mean? Unimodal sense means they're only working on, say, only from videos, RGB data, or oftentimes only for skeleton joint position data. But we figured that in our case, human action is inherently multimodal. It is, if we are looking at just one modality data, we cannot actually capture the whole breadth of information that the other modalities can give us. Just to give you an example, say if we are verbally saying that bring me that book, and you can see those two books there, almost impossible for you to perfectly determine which book that I'm talking about. Instead, like if you are just looking at video and audio data. But if we have a gesture there as well, which is a person is pointing to something and we're saying, bring me that book, you obviously understand that we're talking about the red book here, right? So that's why we need the multimodal information, and we need a way to fuse all those information together so that we can utilize that for the activity recognition. So we have developed several models for human activity recognition, which recently have been published to AAA, RALP, IROS, and we have also some submitted papers. But today I will be talking about our work that recently have been published to IEEE Robotics and Automation Letters and ICRA. We call this multi-GATE, graphical attention-based hierarchical approach for human activity recognition. Instead of going too much into detail, let me just briefly give you some overview how this model works and our rationale to choosing these model parameters. Multi-GATE is a hierarchical model, a hierarchical architecture it has. First, it has an encoder layer, which encodes spatial and temporal features. Then we are using a multimodal mixture of expert, or in other words, we're calling it multi-MOE. And this, what is the purpose of this multi-MOE is to extract the modality specific salient information for each modalities. Then the challenge comes how to fuse those information. We now know that what are the important information for each modalities, how to fuse that. To do that, we proposed a novel graphical attention based approach. We called it cross-GATE, which utilized which generates a graph based on each modality data, and then put graphical attention on those salient information that we are getting from the multi-MOE features, and then fuse those together for the task learning layer. In our case, task learning is the human activity recognition. So just to give you an overview, first the encoders, which takes all the data from various modalities, say from video, from skeleton data, from depth data, and maybe physiological sensing data. And for each modality, we have encoders, and we are getting spatial temporal information from there. Then in the multi-MOE layer, we extracted the modality specific salient information, as I mentioned, that which are the most important information for each modality, spatial temporally. And then we use the cross-get, which is we're putting multimodal self-attention, multimodal graphical self-attention, where the idea is if for each modality, given its the features, it's asking all other modalities, okay, these are the features that I think from my modality that I'm seeing are most important. Can you, the other modalities, give me what, given my features, can you tell me what are the most important features that you guys, modality can send me? And then utilizing that, it put an attention mechanism to fuse those information into the feature space. And then it you use a feed forward task learning network with those features. We validated those on 3 activity datasets, multimodal datasets widely used, AMAC, UTD AMHAD, and UCSD MIT datasets, which had like multiple modalities, including video, depth, acceleration, gyroscope, orientation data. And our results suggest that like we outperformed all other methods from the literature in all the evaluated conditions. So I'm skipping those and I'm coming to some important and interesting findings that we saw. First is the impact of modalities. So one important thing is for multimodal fusion is, does multimodal fusion means that it always can generate a better representation? This is an important question because oftentimes if your model is not capable of handling multiple information from multiple modalities efficiently, it might generate some noise into your feature space. And as a result, your task learning efficiency, that means like your accuracy, might decrease if your model is not strong enough to handle multiple modalities intelligently. So that's why we tested in this space where we started our model training with RGB and skeleton, that we incorporate physiological sensing data. Then we incorporated the depth data, and we wanted to see whether the model can handle the increment appropriately. We saw that yes, our model could, and we found that like multi-get outperformed, but this is not the case for other state of the art. So what it indicates that the other models, Hamlet and PLS in this case, probably are not capable of handling and extracting the most important salient features from those modalities. And another one is, as we are thinking about real world deployment of these models into the robotic systems, if we are assuming that we will always get the pure data from all the modalities without any noise, then actually we are assuming it wrong. Noise will always be a part of our data. So we wanted to test like how it works, our model works into noisy data. And we've figured that like even if we have noisy modalities, our feature extraction part can still find out a robust representations of the features. And results indicate that as well. And overall also, if you are looking at into the feature space, how the representation looks, if we're comparing against two other approaches like non-attention based approaches and unimodal attention approaches, we can see that for two activities here, throw and lunge, we can see that the representations are overlapped, Whereas for our case, the representation is separated. That might indicate that like the features are more robust in the sense of classification.
Quick question for you. Liang, did you want to ask the question?
Yeah, sure. Thanks. Interesting. I kept thinking about all these results, how to interpret it. So the results in terms of accuracy about 97%, that's quite impressive. So I'm wondering, how do I interpret 97? What does it mean in the factory? So can I say, hey, we have a accuracy of 97% to detect there is a human operator within very close proximity, or maybe in some other sense. So that means, let's say 99, 98, 97, how do we interpret it in the physical world?
Yes, so I think it is top one accuracy, right? So it I think like one of those were F1 score probably, but I cannot remember like which one is F1 score. So what does that mean? That means like 97. If it is top one accuracy is like as we know that from the confusion metric, like we can assume like how accurate our predictions are, right? Like this activity is predicted correctly. This activity was not predicted correctly. Does that answer your question?
Yeah, somehow I think I get the point. Yeah, thank you.
Okay, yeah, but I think like we did also F1 score, but probably I'm not showing it here. And F1 score is a more robust representation, which can combine the accuracy, precision, and recall.
Yeah, actually, I think maybe later you very likely you cover a follow-on question is, let's say, excellent method, and then how about, let's say, deployment? Like when can we how can we deploy this thing? Let's say, do we need the modification or any improvement of existing robot arms or anything, something like that? But anyway, yeah. So
yes, absolutely. I would be that is a very good question, and I'll be more than happy to talk about that as well. Like how can we make this real world deployable?
Yeah, definitely so. Because
yes,
right now the limitation there is, hey, GM do not want to stop their manufacturing, right? They do not want us to add anything there to modify the hardware, and that's we have good technology, but the deployment is another dimension of challenge.
Right. Yes, exactly. Yes, absolutely. You are spot on. Right. Yeah, that is the challenge, and I will be probably in the later part. I will be touching a little bit about that as well. Like how can we make this deployable in the real world setting?
Yeah. Thank you.
Yeah. Thanks. Good question. Thank you. So so as I mentioned, this is about the representation and perception part. Now comes into the prediction, like how can we utilize this kind of knowledge and predict or like in general predict human motion, right? Because this is very important for robot to achieve anything, any sort of actions needs some sort of prediction. So how we pose this prediction problem? So we are posing this prediction problem based on some observed frame. Can we predict where the human will be in time horizon as well as in space? So we are saying time and space where the humans will be. I'm saying here humans because maybe the robot might need to work with multiple humans and the robot might need to predict multiple humans at the same time. But human motion prediction is challenging, of course, and because the stochastic nature of human can move abruptly. Its motion are not always predictable. Additionally, human motions are not always optimal. Like we are making many motions which are not optimal in the sense that it's not shortest distance, for example, right? It might be a little curvy. So how can we predict all those motions for robots to understand? Additionally, when multiple humans are into a team, there are lots of collaboration and inter-agent dynamics going on there. So it's not that one agent's motion only depends on the motion of that person, but it also has influence from the other agents from this team. Can we capture those inter-agent dynamics when we are predicting or anticipating the motion of other humans? So this is the challenge that we're trying to address, and we also have done quite a bit of work in this space. And today I'll be focusing on mostly one of the prediction models that we proposed. So this prediction architecture also depends on a variation of variational autoencoder. So what we're doing here is we are also doing an encoder architecture to encode the motion features from human motion from observed frames. Then we have a latent space where we are trying the objective of the latent space, as many of you probably know that from variational autoencoder architecture, the latent space actually tries to capture various like motion parameters by somehow modeling those with some random variables. And then we use a decoder which utilizes this latent variable or latent space to predict in different ways to where the what the future frames or future trajectory of the human would be. So just going through again very quickly is first encoder to encoding human motion parameters. We're doing not only positions but velocity and acceleration of each human joint positions. In this case, we are only focusing on human body movements. That means if we are using Kinect sensors, then Kinect might give you 20 body joint positions, and we are looking at can we predict where those all 20 joint positions will be. If we are using motion capture system, it can be very similar, and we even can utilize RGB cameras and utilize open pose to get skeleton joint positions to find out where the humans body joint positions are. Then using the, we are putting a temporal attention mechanism here, a spatial temporal attention mechanism to extract important spatial temporal features. Then we use a latent space. The latent space is, as I mentioned, to capture the motion dynamics into latent with some random variables. In our case, we are utilizing continuous and categorical latent space or latent variables, and the rationale between that is some motions might have continuous parameters, and it also might have some discrete parameters. For example, temporarily we can probably discretize motion that might be captured by the categorical variables, whereas continuous motion could be continuous latent space could be capture the continuous parameters of the motion. And to do that, we use adversarial learning, and I'm not going into detail how we did it. And then comes our decoder, where it utilizes the latent space variables ZT and CT, which is continuous and categorical random variables and past observations, and auto-regressively can predict what, where, and where the humans will be in time and space. So the good thing about this architecture is can be easily extendable, and we did for multiple agents, where the latent space can encapsulate the motion parameters of multiple agents. So we are not saying that it explicitly did, but it has some sort of underlying capability to capture various motion parameters together. That means when it's encapsulates all those together, there might be some interaction between those. That indicates that it might be able to capture the inter-region dynamics, not explicitly, but maybe implicitly, when it's utilizing that in the temporal decoder for predicting multiple humans' motion. And we evaluated that extensively on various data sets, to be precise, 5 experimental conditions. And we used mean squared error of each joint position in centimeter as our metric. So that means like if we find it's lower, that means like we are finding it the prediction is more accurate. And we tested on all of those, and we figured that like our method showed and outperformed all other methods from the literature that we tested against. But I'm skipping those and coming to some interesting results, qualitative results that we found are more interesting. So for example, now let's think about like 4 activities. Humans is doing 4 activities: walking, jogging, bowling, and lounging. And we want to see what our encoders can capture. We figured that these are the encoded message in the latent space. It's actually the continuous latent variable. If you're projecting it into the 2D space, these are the representations that we get for these 4 activities. So we can see that walking and jogging, which are very similar in nature when we are doing this sort of activities, it has a very similar representation. Whereas bowling and lounging are very similar activities. Like the person needs to lower their body joints a little bit to bowl as well as lunge, and we see that they also have a very similar representation in the latent space. But as these 2 groups are a bit different from one another, one is walking and jogging group, another bowling and lunging group, we saw that in our latent space they also have like separated distributions. And which we found very interesting and insightful, because maybe if we can utilize this kind of knowledge for unknown activities later, right? We can utilize a similar type of encoder and similar type of representations, and instead of labeling those explicitly on what kind of activity that is, we probably can from the our algorithm can figure that out, what kind of activity is that, and based on that we can utilize that knowledge to make any decision on that. So this is the prediction part, and which we figured that like our prediction algorithm can more accurately than the methods that we tested against to predict where the human will be in time and space. Now it comes to the robot, how the robot can utilize those kind of knowledge to interact closely with human, right? So just to give you an example, like maybe a robot can predict what kind of materials or tools in an industrial environment a human might need based on like what kind of activity human is doing, and then bring the object to the human when the human needs it and hand it over to the human. To do that, the robot needs a prediction about where the human will be in time and space, so that the robot can essentially deliver the object to the robot. We also have done several collaborations here, and I previously collaborated with Honda and Steelcase, where we deployed robot in their assembly lines to help humans to support their workers in the assembly line. And particularly, we are interested in to say this is an assembly line currently. A person, we are saying 3 tables. Actually, it's a moving assembly. person is doing something, then the person needs to go to pick up a part, come back, assemble it. Next thing comes, needs to go back, pick another part, assemble it, and it moves again. Our goal was, both for the Honda and Steelcase, was how can we assemble a robot there which can predict what humans will need next based on what human is currently doing, and then go pick the part, bring it to the human when the human needs it. So human doesn't need to go back and forth multiple times to pick it up. And humans motion like that in the assembly line is called net B work. It's an industrial term which essentially means waste of their labor. And companies are always keen to minimize that. And just saving 1 second like that might save the companies several $1 million. So companies are very much interested doing that, and we were interested in, can we make a robot to help the human to perform that task better. We have recently also a project with the Virginia Commonwealth Center for Advanced Manufacturing in a similar line of research, where we are also trying to deploy a robot into the assembly line. So I'm talking about the work with Honda that we did. The goal was, can we enable a person to assemble a dashboard? Can we enable a robot to help the person to perform dashboard assembly better? So in this task, if we very coarsely divide, the person first needs to go to the dashboard, scan it, come back, picking up the meter, come and assemble it, go to the navigation unit, pick it up, come and assemble it, and then exit. The exit and first coming, it's just to discretize each activity, but when it's assembly line, those activities are actually overlaps with the last one. But this is an overall scenario what a person needs to do. So if we are looking at this, what we're seeing is the person is making this kind of motion, this kind of movement. The person is going multiple times to the dashboard, come here, pick it up, come back again, and doing that. And as I mentioned, these are considered as net B activity into the assembly lines. So our task was, how can we reduce this? Instead of going into detail of the perception, prediction, and then how we did the decision making here, I'm just keeping that part as and those can be found in the paper. But here I just want to show a video that we produced emulating the Honda assembly line into our lab environment. That is only because we also did a similar deployment in the Honda testbed factories, but because of IP issues and everything, we cannot show and get any data from that. But we generated a similar video into our lab environments, where you can see a person is going to assemble something, and our activity detection algorithm right away can detect which activity the person is doing, even looking at only a partial trajectory. That means only a few frames or a portion of the frames of the initial activities, and utilize that knowledge for the robot side to make the navigation plan, go there, finding a grasp plan to grasp the object and bring it to the human, and make a handover plan and hand it over to the human, so that the human doesn't need to go back and forth. In this case, you can see a discrete activity where human does the whole thing in one round, but you can imagine that it can happen multiple times, and the robot can keep helping the person. So yes.
Tariq, can I ask a question? Because it
yes,
seems very, it's very interesting. I'm trying to understand, this is so heavily driven by computer vision and the ability of the device to either in real line of sight or some other, ultra wideband mode detect where the human is. And how often do you, and how, I guess I'd ask at the highest level, how do you deal with the environmental conditions, whether there's an object in the way or whatever it might be, detection algorithm, that the robot doesn't have sufficient visual and results in, I guess, a false negative or something like that, versus, you know, if it's a more dynamic environment, you can imagine times where it would be very difficult to locate the human.
Right, exactly, Doc. That's a very important question, like how essentially we work with the perception part. So as I mentioned, like we are doing a little bit of work in the perception side, and we are thinking that we're trying to develop perception algorithms which are robust to noise. Because as you mentioned correctly, that like robotics vision and robotics sensing will always be noisy. So we need something which are more robust. That's what like we're working towards, making a robust algorithm for utilizing and capturing the like disruption into the environment. But also oftentimes when we are trying to, like, for example, in this case, we are trying to make sure that perception, the failure in the perception algorithm does not impact the whole architecture in the robot side, like robots decision making, where when we're testing the robots decision making parts and everything, we skip the perception part and utilize oftentimes the motion capture system just to test the robot's decision making process. In this case, what we did, we use a motion cap system to track the human's motion. But for the real deployment, yes, that is obviously the most if not the most, one of the most important problems needs to be handled, the perception. But did I answer your question?
Yes, it did. Thank you.
Yes, thanks. Okay, any other question? If not, like we are also doing a similar project with, as I mentioned, with CCAM here at Virginia. And we also did, as Doug, you mentioned, with environmental change. We have just recently submitted a paper, and I have some videos, but not in this presentation, is where we are actually changing the environment. If we're changing the environment, can we transfer the knowledge? That is the most important thing that like we are investigating in that paper, that we are trained on a non-cluttered environment. If there is clutter in the environment, which would be obviously visible from the video data, can we still transfer that? That is the goal of the paper that we just recently submitted. And we found some interesting result. Our method can. And we are we are very excited about that as well. And with that, I would like reiterate the projects that we're doing, and I'll be happy to chat about the other projects offline as well, if you have interest on those as well. And I want to, of course, thank my grad students who are actually doing the work. And with that, I want to conclude the talk today. But I'll be happy to take any questions that you might have.
Thank you so much. That was a very interesting presentation. Lots and lots of very hard problems and very applied. That's what I like that about this work. So very, very neat work. Do we have any questions from the students or from the faculty or staff who are in attendance?
I have some question. Doug,
well, let me first say I want to thank Ashish for bringing Tariq to our attention and recommended him as a speaker today. So thank you.
You're most welcome. Actually, great to see Tariq. Nice seeing you. And also thanks, Doug, for inviting Tariq for this talk. I mean, this is amazing. Actually, very impressive collection of work, very, very impactful in everyday use cases. I have a couple of questions. Doug, do we have time?
Yes,
Yes, we do.
Okay.
At least ask one or two, and we'll see if
Yeah,
Josh or
one or
others
two,
have questions.
should be fine. Thanks, Tariq. So a couple of questions actually from the last couple of projects that you mentioned. One is actually the video that you demonstrated that the robot is following the human intention. So using motion sensing device or the RGB based systems.
Yeah, so in this example, Ashish, like we use motion cap. We use motion cap just to avoid the perception problems.
Okay.
Yeah.
Okay.
But like we now have the perception capabilities to plug into that, like which we did in our recent project. But I'm showing a little older video that we did with Honda.
Yeah, I mean, a couple of results that you mentioned for perception.
Yeah.
I saw gates. I mean, for this sensing, actually, did you convert or translate everything into gate-based analysis, or you still are using, say, CNN-based prediction?
Oh yes. So like in the initial models, that like a perception, and that's what you are asking.
Yeah, I mean.
Yeah. So sorry, Ashish, go ahead.
No, I mean, so I would just like to know actually whether these intention detection is purely based on gate analysis, or you still have RGB based vision or image processing involved.
Yes. So yeah, like instead of this one, let's sorry about that. So
Kyrgyzstan ethnic national groups clashed
Hello?
with each other over the division
Yeah, we
Yes,
can hear you. Sorry
I can
about
hear
that.
you. Somebody else has
Oh,
something running. I don't know who it is.
Okay. So yeah, sorry about that. So what I was saying, like in the perception work, it is based on multiple modalities that I mentioned. Like let me quickly show. Like it's if I can go. Oh, okay. So if I can share my screen again. Sorry about that.
No problem.
Yes, yeah. So for these data sets, we tested against, and this data set has RGB and 4 RGB views, acceleration, gyroscope, and orientation of the human. And these data sets RGB depth, skeleton, and IMUs, skeleton, SEMG, and IMUs.
Yeah, great. Thank you. So yeah, this is actually a good answer. So I mean, so back to one other, the very first project that you mentioned involving multi-modality. And also you saw that actually it's a synergy that actually if you add more than one modality, your performance improves. It's a little bit counterintuitive in a way. Sometimes actually, depending on maybe you got lucky, and I just want to emphasize that maybe did you consider some analysis on interference or weights? Did you train based on actually, is it just the plus addition of all this modality, or this is a weighted sum of something? Because actually adding more modality, I mean, it's a data integration problem. I mean, might not actually, by looking at the other competing algorithms, you saw actually the trend might be different.
Right.
I'm not sure actually how you tackle that kind of thing actually. I mean, whether these modality are equally contributing into the prediction or not.
Yeah, that is an excellent question, and you are spot on, right? Like additional modality does not guarantee always to be better. Does not guarantee that we get a better representation if we are adding more modalities. That's why like we need to be cautious, and we assume that like our method, if we are going back again a little bit, it is not a like concatenate of all the modality data that we are getting. we are doing here is graphical attention. That means we are asking the additional modality that, okay, from the existing modalities, this is the representation we are getting. So can you give me what additional information or like complementary information that you can provide from the additional modality? So that is important, because that gives only the important information and complementary information from the additional modality.
Okay.
So that's how we can see, and we also assume that additional modality only provides good information, and that's how we probably got an increment in with additional modality, which might not be the case for other algorithms.
Yeah.
And we tested it also like with noisy modalities, like we incorporate noise into the train and test, and we incorporate train with non-noisy data and tested with noisy data as well. And
it is a clever solution. I mean, you use the good part. I mean, so probably the self-attention did help. Thanks. I mean, Doug, I mean, just one last question is, I mean, the third stream of research that you mentioned about the human-robot trust. This is, I mean, you said actually that your projects are more involved into calibrating the trust. I mean, it's very, very relative term given the project.
Exactly.
I mean,
right.
So how do you quantify trust? I mean,
trust,
is there a measure?
Right, exactly. Very good question. And
you can answer it maybe, I mean, the way that you want, but I know maybe there might not be an answer, but we can talk about that maybe later. We have of time, but go ahead.
Absolutely, like Ashish, like I would be more than happy to discuss about like this as well. But like to answer your question very briefly, there is a whole bunch of literature in the trust, like what in the human trust, like what is trust, right? So there are many definitions of trust, but in our case we need to make a pick a definition which suits our problem space. And we are assuming by trust is the perceived trust on the capability of the robot. So what does that mean? That means like if I am trusting the robot can do a particular task that I'm thinking the robot can. This is how we define trust. So yes, you are absolutely right. We are narrowing down the focus of trust to a particular definition for our problem space. But it's absolutely
so that's reasonable. Thank you, Tariq, for all these questions and also coming down and giving this talk.
Oh yeah, it's my pleasure. Ashish, thanks.
I think that Nang has a question.
Yeah. Sorry, I have another question.
Yes.
But again, the question is not.
Nang, you're muted.
Not muted. He just went off.
Network, probably network.
Oh.
Task, right? Pick up different objects and.
Sorry, Liang, would you mind like saying the question again? We could not hear you.
Yeah, I think I have some connection. Is it getting better?
You're better now.
Good.
Yes, we can actually see you now and hear you.
So my question is, why you came to that testing scenario to get started for this test, right? It's more like an assembly operation. And I believe that there is a practical value because you mentioned that in Honda you also have some related. So that means Honda must believe this is some kind of really important scenario, right? And the reason why I came to this actually is more like we're talking about a cobot, right? A collaborative robot.
Yes.
What are the typical difference in terms of the application scenario in a manufacturing factory that cobot can do, but traditional automated assembly line cannot? So so it's two questions, but actually related, right? So
that's again a very, very important question, right? Like how we define that, like it all things can be automated, or how can we define that this can be automated and this cannot, and where we need the robots? I'm just rephrasing the question a little bit. We did a lot of work on that as well, and we came to the conclusion we need humans to be there. For example, humans, why we need humans there? We need humans because humans are the most expert doing this task for a long time. They're the apprentice, and they have the most knowledge about doing it right. For us, that's why we need humans for sure. Then we define that we need human, but we need robots to help the human to perform humans' tasks better. Then we need a division between tasks of humans and the robots. What kind of tasks humans are good at, what kind of tasks robots are good at. We did some analysis there, and we figured humans are really good at fine-grained manipulation tasks. Like humans are very keen at, like the video that I showed earlier. If you look at this video, you can see humans are good at and doing so that fine-grained manipulation, like putting a plug inside the dashboard, going there, which is, in my opinion, are very hard for a robot. Like this, doing exactly what the human is currently doing, is very, very hard for the robot. Robot cannot do that. If we make want a robot to do this, it would take a decade for robots to be perfect at this. We don't need that. What we need is, we want humans to be there. We want to keep what they're really good at, and we want to take out the activities that humans are often not good at, or those are not beneficial for their health, to pass it to the robot. We did a lot of surveys into the factories, Honda, and also, as I mentioned, on Steelcase, and we try to figure out what activities are not perfectly done by the human. And human choose, in our case, if I am coming back again to the experiment that I showed, I apologize for skipping the slides one by one instead of choosing one. So we figured that after doing the interviews, we figured these motion tasks are not what humans are good at. Instead of good at, we will say that humans not the best performing those tasks. Additionally, one additional thing that we found, but I didn't mention here, was oftentimes these beans, meter beans and navigation beans, are stacked over one another. So you have, as a human, you have to lean forward to take objects from those boxes, which are often injurious to them. And this is explicitly defined by the workers into those plants. And they say that, okay, this may be the task that the robots can do. That's how we divided the fine-grained manipulation and gross motion task. Fine-grained should be the human, gross motion should be the robot as the cobot, and we want both to work together instead of automating everything.
Yeah, thanks. I think that what are humans good at and not good at, that's the key information I'm looking for. Thank you.
Okay, yeah, no problem.
So any other questions? As was mentioned by one of the students in attendance, this is pretty heady stuff, and a lot of background needed to kind of wrap your head around it. And I think it just speaks to the complexity of the problems that you're trying to solve. So thank you so much for speaking with us today. Maybe we can have you come out to campus at some point and present. What do you think?
Absolutely, I would love to come I never been to Colorado, to be honest. I have been to the airport, so that should not be counted. But
that doesn't count.
Doesn't count, sure. Yes, I would love to. Yes.
Great. Thank you again so much.
Yeah.
Bye,
Thank you,
everyone.
everyone. Yeah.